Welcome to the Forces in Motion final review. Obviously, our physics unit was pretty complex, but I'm boiling it down to just a few things that you need to know for the final exam. What you're looking at here is actually what we call a force diagram or a free body diagram. You did see some of these on the physics test, and basically all this shows is there's some object shown in red in the middle, and it's showing you what forces are acting on it in 4 directions. So let's say that the object is resting on the ground, and if that's the case, then the weight of the object gives it a force downward, right? Its weight, which is caused by gravity, we're saying is worth 15 newtons approximately of force. And remember, N for Newton is how you measure force. Force is measured in those weird units called newtons. So there's 15 newtons of force on the ground because of the object's weight. The ground is pushing back against that object. If it weren't pushing back up with exactly the same number of newtons of force, then the object would be falling through the ground. So the forces are what we call balanced in this direction. Balanced forces means no motion. But in the left-right direction, the forces are not balanced. There's more of a push in the leftward direction than there is in the rightward direction, for a net force of 2 newtons left over in this direction. And forces have an amount that's associated with them, the 2, and a direction, which is the arrow. So we've got 2 newtons of force pushing on the object to the left, which means it's going to move to the left, and how quickly it moves to the left can be determined using an equation that we'll talk about a little later. So what is motion? Well, motion is what happens when the forces acting on an object are either unbalanced, so that motion happens, or the object was set in motion a long time ago and it's continuing to move even though all the forces are balanced. So when an object starts to move, we say that it picks up speed, right? Or it accelerates. So there's a lot of confusion among these terms: speed, velocity, and acceleration. Speed is just how fast something is going, and you can calculate it by taking the distance it travels and dividing by the time it takes it to travel that distance. Velocity is almost the same exact thing. Notice that the formula appears the same. It's distance divided by time. But technically, for something to be called velocity, it has to include the direction you're traveling in. So for example, 55 miles per hour is your speed. 55 miles per hour to the west is your velocity. And that's really the only difference between those two things. Where people get confused, though, is with acceleration. Acceleration is the change in your velocity. Are you speeding up, slowing down, or changing direction? So you're accelerating if you speed up, slow down, or change direction. Keep this in mind. Because acceleration is a measure of your change in velocity, and because velocity includes direction, if you maintain a constant speed, but you're going in a circle, you're accelerating. So if you're on this track and you keep going at exactly 5 meters per second, that's great. You might say to yourself, oh, I'm not accelerating. Well, you're not speeding up or slowing down, but you are constantly changing direction, and therefore, technically, you are accelerating. On your final, I stick to very simple word problems for calculating speed, distance, and time. I don't believe there are any acceleration word problems on your final, but the definition of acceleration is there. So you need to remember that acceleration is a change in velocity, which could be speeding up, slowing down, or changing direction. Remember the roller coaster? Roller coasters go through a series of loops and turns and hills, and as a result, KE and PE are always changing. KE is the kinetic energy. That's the energy of motion. And PE is the stored energy, the potential energy. So if you were to see a diagram like this with 4 points labeled on it, I could ask you, I could say to you, put them in order of who has the most potential energy, starting with the most potential energy and ending with the least potential energy. Well, On a roller coaster, all the energy is stored up as a result of your position above the ground. It's all got to do with gravity. And the further from the ground you move the coaster car, the more potential energy you're storing up, and the less kinetic energy you actually have. So at point A, we have the greatest amount of potential energy because we're the furthest from the ground. At point C, we're we're lower than A, but we're above B and D. So that would be the next highest potential energy point. And it looks to me like D is above B, so it would go in this order. A has the most potential energy, then C, then D, then B. It's kind of the reverse with kinetic energy because the two types of energy convert into each other. So if you have a lot of potential energy, then you don't have very much kinetic energy. And if you have a lot of kinetic energy, you don't have much potential energy. If you're somewhere in the middle, then you've got like equal amounts of both. So as I said, point A has a lot of potential energy, but it's just starting to move, so there's hardly any kinetic energy at A. So if I were putting these in order of highest to lowest for kinetic energy, and let me just label this. This is the potential energy is going down as we go this way. Let's do the same thing for kinetic energy. We would say that the most kinetic energy is at the lowest point, which is point B. When we're on the ground, all the energy that was stored up has been released. We're now moving at our fastest speed at point B. Then at point D, we're pretty close to the ground. That's our next highest point. So again, at point D, we're going pretty fast. Not as fast as we would be at B. At point C, again, we're close to the ground, but not on the ground, so we have less kinetic energy there, and we have hardly any kinetic energy at point A. So the two things are reverse of each other, right? This one goes ACDB, this one goes BDCA. And those are exact opposites, you can see, right? The A goes there, the B's go there, and so on. So kinetic and potential energy are always being converted into one another. Remember that potential energy on a roller coaster has to do with gravity, so the further from the ground you are, the more potential energy you have. The closer to the ground you get, the more kinetic energy you have. Another thing that comes up in the physics unit is the difference between mass and weight. Here on Earth, we use the terms almost interchangeably, and that's okay because on Earth, by agreement, your mass and your weight are equal to each other if you're using the unit kilogram. However, if you were to change your location significantly, go to the moon or to Jupiter or something like that, your mass would stay the same because your mass is really a measure of how much you resist being moved, but your weight would change. Weight has to do with gravity. If the amount of gravitational force acting on you changes, your weight changes. But your mass doesn't, because your mass has to do with how many particles make you up, and give or take a particle or two, you're not really gaining or losing very many particles as you move around from location to location. However, if you get significantly further from the center of the Earth, your weight will decrease, and if you go to a planet that has more gravity, or to another object that has even more gravity, like the sun, then you're going to weigh even more. So when you're on the moon, you seem to weigh less. But that doesn't mean that you're easier to move around. You're easier to lift, but not to push, because your mass stays the same. So you can see in all these pictures, no matter where you go, your mass is always 63.5 kilograms. But your weight keeps changing, depending on whether there's more or less gravity. On Earth, the weight here is about 623 newtons, which equals about 140 pounds. And then on the moon, you can see that the weight drops significantly. You only weigh 23 pounds on the moon. But, that would mean that it would be a lot easier for me to lift you up off the surface of the moon. But if I wanted to push you in a straight line, I would still need to use as much energy as I used before because your mass is the same. So mass and weight are different. The last thing that comes up in our physics unit are Newton's laws. There are 3 of them. So you can see all 3 represented here. This is Newton's first law, or the law of inertia, which says that an object in motion stays in motion until acted upon by an outside force, or an object at rest stays at rest. Basically, this is the seatbelt deal, right? If you hit the brakes on the car slows down, but you keep moving at the speed the car was going. And if the seatbelt weren't there to stop you, you'd go right through the windshield. That's inertia, or law 1. Law 2 is this formula, F equals ma. The more force you exert on something, the more it accelerates, assuming, of course, that it's the same mass both before and after. So you can see these two blue spheres are the same mass. They look roughly the same, and we're hitting them with different amounts of force. Those are the orange or yellow arrows there to the left. And as a result, they accelerate differently, right? The one that we hit with more force accelerates more. Very common sense. And then last but not least, this one over here is action-reaction, or law 3. So this one here is 2, and this one here is 3. For action-reaction, for the definition is that for every action there's an equal but opposite reaction. And you have to remember that action-reaction pairs are forces that act in opposite directions on different objects. So the air is coming out of the balloon, and as a result, the air is pushing against the balloon, and the balloon is pushing against the air, and so the air goes one way, the balloon goes the other way. So that's it in a nutshell for the physics recap. See you guys in class.